as Margaret just said, I work in the respiratory and inflammation research area within AstraZeneca. We have several research areas. This is going to be a very personal perspective to respiratory and inflammation. And I'm going to actually describe this. The way we use human tissue in drug discovery is obviously more difficult in certain research areas like CNS, where it's a lot harder to get tissue to use. This is our story, if you want. As I'm the token big pharma person speaking here, I'll just put up a schemagram of how drug discovery is done. In the industry, most companies will have something that looks like that. We start with an idea for a new medical entity that hopefully will address an unmet medical need. So at this end, and hopefully ultimately we come out with a drug. There's a number of processes along here. We do early target validation. We then run a screen, identify compounds, and we continually optimize these compounds till ultimately we get to the clinic and we test the hypothesis in the clinic. I work very much at the early stage of the pipeline along this end, the idea generation and early validation. And I should say that our earliest milestone is actually, this is dead completely, is to run a high throughput screen. And even when we turn up with a proposal to do that, we would be expected to have a significant amount of human tissue data in that package to actually convince people it's worthwhile looking at this target. So why do we use human tissue? Well, a lot of this has been covered and it's fairly obvious. Well, the first obvious one, we're aiming to develop drugs to treat human disease. So using human tissue is an obvious way to go. Bob mentioned this earlier. The expression and function of drug targets in humans may differ from animals. In many cases, these animals are good models, but there's lots of instances where they're not. The target may not even be expressed in the animal, or it may have a completely different function. And you can use things like immortalized human cell lines rather than primary cell lines, but they're not particularly good surrogates for human primary cells. They're better for cancer cells generally, which are where they're derived from largely. Sources of human tissue, what do we use at AstraZeneca? Well, various sources start at the top, and we extract various cells from the neutrophils, monocytes, T cells, etc., that we can use locally in our experiments. We can use commercial sources, people like Promocell and Lonza. You can buy various primary lung cells, for example, so lung epithelial, endothelial cells. You can use companies like AZamended to do experiments for you, etc. But we have various collaborations with clinicians as well, and we have a number of these set up, and they basically access a range of things from blood, sputum, bronchial lavage, urine. A lot of these are used for biomarker analysis, and then lung tissue, which has been talked about earlier. We use a lot of cancer resection material. We do get transplant material from COPD patients. That's a lot harder to get. And we can get biopsies and nasal brushings and things like that. And we can use all of those in our experiments, and we do. What we're using this tissue for, what information can it deliver? Well, first thing, it can give us a better understanding of disease pathophysiology. That's quite important in a lot of the diseases we work in. Things like COPD are relatively poorly understood still. So we can use this tissue to increase our understanding of that. The second one, as I alluded to earlier, we're trying to generate evidence that drug targets are important in human disease. This is all about building disease linkage. We want to know that the target is expressed in the disease tissue and in relevant in vitro systems that we may derive from that tissue. And then more importantly, expression is great, but what really matters is function. We want to do functional experiments on this tissue and actually come up with evidence that the target's involved in a process that's implicated in the disease pathophysiology. We can also use tissue to compare new drugs with drugs that are used in standard care. Is this drug likely to have a better efficacy profile or than things that are already out there? And the last one, we can use the tissue to investigate key mechanistic safety risks around the particular targets. Now what I'm going to do in the next few slides is illustrate examples of all of these. So understanding disease pathophysiology, this is some work done in collaboration between AstraZeneca and University of Mainz in Germany. And it's a combination of a CT scanning experiment down the bronchial tree and some histopathology. So on the left-hand side here, that's a bronchial tree. This thing is really bust. And basically, there's been multi-slice CT scanning done there, and that's an image in the black there. And you can see the airway with the green thing going through the middle, which is the bronchus essentially. And what they've done is compared never smokers and smokers with COPD and looked at the wall thickness in these patients. And over on the right-hand side, you can see that if you're a smoker with COPD, your wall thickness tends to be thicker than if you've never smoked. And what they did is also take 11 of these people received resection, and we did histopathology in those resections, and then looked at the histopathology in these as well. And what was seen in the small airways, you see largely a fibrotic phenotype, and as you get to the larger airways, you get edema and inflammation. So it tells you a bit about the diversity of the changes that are occurring down the airway tree in COPD. Moving on to improving disease linkage, this is the sort of stuff I spend my time doing. As I say, we do a lot of work in COPD and we do access lung tissue. We've had a couple of collaborations delivering transplant lung, and you can do a lot of things with this. So you can obviously take histopathology samples and and learn more about the disease that way. But we spend a lot of time isolating various cells from this tissue, whether it be fibroblasts, type 2 cells, microvascular endothelial cells, alveolar macrophages, etc. And we use these to do functional experiments on, as well as to look at expression in these systems. Moving on to the sort of data we generate when we're looking for new targets. I mentioned target expression. That's something we're particularly interested in when we start to look for a new target. And this is just an example of a GPCR, a G protein coupled receptor, that we're interested in. It's reported to be highly expressed on the monocyte macrophage lineage, and this experiment here, just a flow cytometry trace, shows that compared with the, I can't really point to anything, compared with the isotype antibody, when you put an antibody for this target, you see an increase in binding and fluorescence of the cells, so that means most of those cells are expressing the target of interest. And similarly over here on the right-hand side, the ligand is expressed highly by epithelial cells. These are two cells interested in COPD. It starts to bring together a story. But is it present in the COPD lung? Well, down below, basically it is. It has the same sort of profile. So macrophages are highly stained for the receptor, and metaplastic epithelial cells stained for the ligand. So it starts to bring together a story that the target of interest is in the place of interest. You could also do things like with human lung slices, and this is a technique that various people have done, and we've had a go at this as well, using cancer resection tissue in this case. So you can take the cancer resection tissue, inflate it with low melting point agarose, it becomes stiff. It's stiff enough then to core, and you end up with cores that are roughly 1 centimetre cubed. And then you can slice that very, very thinly, and you can look at histopathology and do functional experiments. What you really want to do is end up with a slice with an airway and a blood vessel in it, as here, there's the airway. And then you can take these systems and do functional experiments. So down the bottom, that's essentially what it is. So here's an airway sitting in a well, just looking down the microscope. It's nicely open, it's dilated, and then you can put things like drugs on it. That's just carbachol, an M3 antagonist, and you get M3 agonist, and you see a marked constriction of the airway. This is important because it allows you to investigate small airways, and small airways are actually things that are important in COPD because that's the major source of the problem. It's not the upper airways, which you can mimic with things like trachea. So these are allowing you to target the area of interest. And lastly, investigations of mechanistic talks. This is an example from the TLR9 area, TOL9 receptor area. There's a lot of interest in TOL9 agonists because they basically they look like good anti-inflammatories. They shut off the production of a number of pro-inflammatory cytokines. Unfortunately, the distribution of this receptor in the human and the mouse is quite different, and a lot of people have done a lot of experiments in the mouse. And you can see there the distribution. So in human, it's largely in B cells and plasmacytoid dendritic cells. In the mouse, it's on those cells, but it's also in myeloid DCs and monocytes and macrophages. When you inhale a TLR agonist in a mouse, you get an anti-inflammatory effect, but you also get a pro-inflammatory effect at not much higher dose. And it's been pretty well proven that that's driven by TNF-alpha production from monocytes and macrophages, and that produces a lung inflammation. So do you want to know if this is applicable to the human system? Well, you get some human alveolar macrophages, and you test your TOL agonist here, which is a CpG, which is lying along the baseline there. It's really done nothing, and compared with LPS, which produces a massive amount of TNF-alpha production there. So you can use the human tissue in that way to tease out whether you've really got a mechanistic tox issue. So the summary of all that, certainly within my research area, we extensively utilise human tissue. We try to use it as early as possible. We'd like to use it more, and we would if we could get more access to it. But such samples for us are really crucial to, one, increasing the understanding of disease pathophysiology. We work in a lot of diseases that are very poorly understood. We need to know a lot more about them. We need to build the disease linkage, and we want to build it as early as we can. One of the previous speakers said it's better to fail early. It certainly is better to fail early because it gets a hell of a lot expensive as you get further down the pipeline. We can use the tissue to compare the effects of new drugs to those using standard care, and that's quite important as well. You want to differentiate yourself from what's out there and what could be coming along. And as I said a minute ago, we can investigate the relevance of key mechanistic safety issues with this tissue. The bottom line is, for us, the data we generate in human tissue is really critical to the identification of new drugs to address unmet medical needs. And that's me finished. Thank you.